Right. Hello, everyone. So for those who don't know me, I'm Sinan. My background is mainly in programming language theory and distributed systems. But for the past year or two, I've been working in quantum computing and quantum mechanics. Things like how do we represent quantum mechanics using concurrency, as well as working with quantum processes where we have multiple simultaneous processes where we have to pass data orders of magnitude in hundreds of gigabytes, sometimes petabytes of data. So if that kind of thing interests you, come talk to me afterwards. But today's talk will not be about this. Today's talk will be about privacy. So I find it important to define what privacy is in a technical setting because there are multiple different definitions. So in the scope of this talk, the privacy will be more concerned with the developer experience and sort of automatically asserting certain constraints brought on by laws like GDPR, and not about the more academic definition, which is differential privacy, where you have an attacker model that has access to your memory. That is not what we're dealing with today. And it was interesting, I wrote a technical paper about this. It goes into more detail about transforming the ASTs and the compiler magic behind all this. You can read it, but I'll try to keep it a little bit more brief today. So let's say we have some social media represented by our little bird there, and we have a customer, let's say Coke. This social media app provides a streaming API. This may or may not be a real API that you're able to subscribe to and say, okay, I want data about my followers and people who interact with hashtag Coke in some way. It can be impressions, engagements, likes, reposts, whatever. And as you get new data about this demographic, I want you to keep sending it to me. So the social media aggregates the user data with some different characteristics like the age distributions, the gender distribution, geolocation stats, and all of that, and sends it to Coke. And some time passes, we get new data, and we send it again. So now let's say that we have a user who doesn't like Coke. I don't know, if their taste buds got burned, they like Pepsi instead. So they say, I don't want my data shared with Coke. Now, according to GDPR, the user is able to dictate with this fine-grained scope who their data goes to and who not. So the social media platform legally cannot send this user's data, whether anonymized or not, to Coke. So the next time you send this data, you essentially have to exclude this user's data. This is a difficult problem. First of all, user preferences can change at any time. If you have some pipeline where especially data is anonymized, it will be very difficult to figure out whose data you should be sending and who not if the user changes their settings like when you're about to send the data. It is also difficult because the user preferences live outside of your application. They live in a database somewhere in a table, and you essentially have to go to that database to fetch the user preferences on like who these blacklisted brands are every time. So now let's zoom out a little bit, and let's say we have an architecture like this. We have some user service, and let's say that this user service defines the user schema, what it means to be a user. And they publish this as a library to multiple services. We have the enterprise data service, which is a service that shares the data with third parties. And we have some machine learning and internal analytics things. So when it comes to legal terms, what you can do with user data internally versus what you can share with third parties highly differs. So like there's pretty much no restrictions on the internal analytics, but there's a lot of restrictions on what you can sell. Then there's the platform service. This is where the user goes to see their own data, and obviously there should not be any restrictions on what they can see about themselves or not. And whenever some privacy change take effect, it has to take effect in the entire architecture, but it has to take effect in different ways. So here are our observations. The decision whether a user's data should be sent to a third party should be deferred as much as possible because these preferences can continue to change at any given time. Two, the user preference data lives outside of our service. And 3, the user data should not exist in its raw form, because essentially what we're trying to avoid is human error, and if we allow the data to exist in its raw form, then all bets are off. Human error still applies. And 4, privacy controls should be centralized. So it should not be all over your application, such that when something changes in law, something changes in your implementation, you shouldn't have to go through multiple files and change a million things. It should be localized to one place where you can make the change and it will take effect everywhere. So how do we do it now? One idea is just brute force if statements all over your application, but as I just mentioned, this is bad. Other than that, we have what we call IFC. This is information flow control. That dictates essentially where the data can flow and where not. So these have some limitations. Mainly, they are very annotation heavy, and they have very significant runtime and compile time overheads. It is also the case that, so some of these work are nearly 20 years old, but they haven't really been used in the industry. And the reason for that is when these were implemented, they were implemented in these small toy DSLs, right? Where you say, okay, I have my primitive types, I have integers, I have strings, and my logic works for that. But it turns out that when you scale this to a full-fledged general purpose language, a lot of these systems stop working. They don't play well with more complex types. So we essentially need something that will work with a general purpose language like Scala. So here's the core observation. Instead of preventing where the data can go, like in IFC, we're going to let the data travel freely inside some secure container. But when you actually try to read the data, we'll impose some set of restrictions. So for those who know me, I love functional programming. I love my monads. And you might say, why not use something like that for this? And we can. We can essentially implement this privacy container that whenever you try to map it or whenever you try to read it, it executes this validate function. Otherwise, it raises some error, which is all good. But this raises a few issues. First of all, some might argue that map is not valid because it is now effectful. There's a side effect in that map. It's not pure anymore. And the second problem is when you do this, you will have to go through your entire application and fix the types. This isn't too bad in a statically typed compile language because the compiler will direct you wherever you need to go, but it's still a lot of work. If you go to a large enterprise and if you tell them, okay, here's my privacy solution, but we're gonna essentially need to fix up all of our code base, they will just laugh and say no. It also raises another issue. When implementing something like a flat map or a product, if this is an applicative, there is this interesting problem of propagation problem. If we have a user type, they have a name, they have email, and they have these lists of interests, what should the wrapper of u.email be? The restrictions I impose on the entire user object will still be valid for the email object, but the email object may have extra restrictions because email is considered personally identifiable information and there are extra laws governing that. So how do you write this monadic container that is able to automatically add these restrictions on the go? And this turns out to be a very difficult thing. So the inspiration of this work is racket contracts. Racket contracts are essentially these lightweight containers around data that allows you to write restrictions on how the data can be read and how it can be mutated. So if you look to the bottom, we have these accessor procedure and mutator procedure that allows us to sort of write these restrictions. This is all good in Racket because the core Racket is untyped. So these contracts are higher order citizens and they are able to travel freely across the application. But how do we get something like this in a typed setting? So let's go through our goals again. Our data should not exist in a raw form. This means that the apply function, the constructor, should automatically be modified in a way that it does not allow raw data. Okay, so we can do something like this. I have my user object, and for each of the fields, I can say, okay, it enforces user personally identifiable information policy, or for the interests, I can say it enforces this user interest policy, and then I can also bind a total policy to my user object. So when you actually do this user construction, it will automatically be in the type of this user privacy policy of user. But, of course, doing just this is not enough, because if you just do this, you'll get something like that. You will have all these misaligned types, and your compiler will complain, and you will have to go around and fixing all of them. And as we just mentioned, we don't want that. But all hope is not lost. If we can prove some sort of equivalency up to an isomorphism between our user object and user privacy policy object, then the compiler can automatically fix up the types prior to type checking. So what this means is that if I have a field on my user object or a method, let's call it name, and it compiles as this, then when I wrap this inside a user privacy policy container, it should still compile. And this is going to be true for all the fields and all the methods. Okay, well, for those of you who like programming languages, this might be familiar. This is just structural typing with some quirks. Scala technically has structural typing, but the syntax is very bloated and it has some restrictions. So I went with a different approach. But before that, we're going to add a few more observations. First, we have to observe that all of our arguments that existed on the original type, as well as the return type, may or may not be also policy protected. So if I have some method m that takes 2 integers, the user should be able to pass a policy wrapped integer to this method or a regular integer. And similarly on the operators, the non-policy protected methods should still be able to accept policy protected arguments. This is important because things like the plus operator comes from the standard library. I don't have access to them to modify their signatures and what types they accept, and same applies for any functionality that I import from an external library. So if I have 5 plus a policy protected 5, that should be the same thing as if both of those integers are policy protected, and all of these should evaluate to a policy protected 10. So when what we're going to do is essentially we're going to go to all of the fields and all of the methods on our types, and we're going to copy them before the type checking happens to our policy objects that are in scope. And this happens 2 ways. If the compiler can decide with absolute certainty that this function f is pure, then it can just copy the function, change the arguments and the return type to a policy protected type, and keep on going. Because the function has no side effects, we are sure that this data will not leave the application boundary, thus it will not leak. But otherwise, we need to wrap it inside this check function to make sure that wherever, in case the data leaves our application, it is safe for it to go wherever it is going. Let it be standard out, let it be a socket, let it be some other API. So we can implement this user interest policy object that extends the policy interface. It has some internal state. It has a check function that returns a boolean. And in this case, it fetches the brands that the user blacklisted from an external service. It checks if the brand that I'm trying to send this data to is contained in this bad brands list. And if so, it returns false, otherwise it returns true. I can also implement this default modifier that says whenever you try to read this data, exclude some parts of it. Because, for example, legally speaking, religious and political affiliations are considered like very, very critical data, and you cannot, under any circumstances, send them anywhere. So whenever you're trying to read this, you should be essentially excluding those. But when we are evaluating these check functions that we have in our policy objects, we may sometimes need extra arguments. And in this specific case, we need to know which brand is requesting the data, which brand I'm sending my data to. But when you're calling, wherever this check function is called, there may be multiple objects of type brand in scope. And this is actually ambiguous. It is very difficult to figure out automatically which brand is the correct brand. So this is where we need the user to annotate a symbol saying, okay, this is where my argument value resides. and they don't have to reside near the function call. They can essentially reside anywhere in the fluid scope of that function call, and the compiler will automatically accumulate that and wire those arguments to the correct call. So if I have a function that is send data, I can say, okay, this argument brand is my policy argument, and this user is also my policy argument, and they will automatically get wired into that check function call, so you can use it in your check function as you see fit. So in this case, when we're fetching the blacklisted brands, we need the user ID, and that gets automatically wired in. We also need the brand that is requesting the data, that also gets automatically wired in. So in summary, essentially the only thing that the developer needs to do to essentially migrate their application to this framework is define their policy classes, which are centralized and can be reused all over the application, update their constructors with the policy enforcement keyword and the correct policies, and annotate their parameters. This is significantly less work than any of the other solutions out there that I'm aware of. Now I want to talk a little bit more about this policy propagation problem, because this is a really difficult and really interesting problem in my opinion. One thing we need to note is if we have a user object and at some point you do field access, member access on this object and say user.email, the policy that propagated to the email field may still need access to the complete user object. Because if you remember here, our check function needs the user ID, and user ID resides in the user object. When you just get the email string, you no longer have that ID in scope. So we need to figure out a way to essentially carry that extra data that we need around as the policy membranes get propagated. And two, in order for the compiler to be able to move these functions to the policy object, it needs to exist before we can actually copy that. And three, we also need to think a little bit about how the policy is composed when we do these member accesses. So problem one is easy. Because case classes in Scala are immutable, we don't ever have the problem of the data going out of sync, essentially the views going out of sync. So whenever I am doing propagation, I can take the original data that I have, I can copy it and place it in the lexical scope of the check function, and it will be able to get used whenever it needs to. We essentially just copy that data, bind it to a newly generated symbol, and we're all done. Problem number two, the policy objects, all the policy objects needs to exist statically when the compilation starts. And in order to do this, this compiler plugin traverses the ASD. For all the method invocations on policy of A, it will generate a new policy for the result type of the method call and insert a new object into the syntax tree for that specific type. So whenever we're trying to find where to copy our methods, we will have that object in scope. Last but not least, how do policies compose on member access? So if I have a user object and a field, a list of interests on it, it may be the case that the parent policy is more restrictive than the field's policy. It may be more restrictive, it may be less restrictive, or it might be the case that they're completely disjoint. So I cannot automatically say that, okay, I want my parent's policy automatically applying to me. Maybe I want something more restrictive. In order to do this, we take advantage of Scala's implicits. We can just define the scope controller, and in essentially the top level of your application, wherever your endpoints are, you can define this implicit scope controller and say, okay, my scope is owner. What this means that I am the user who owns this data, therefore there should not be any restrictions. And if that is the case, in my check function, I can just use this implicit argument and match against the value of it and say that, okay, if the owner is requesting this data, I don't actually have to run this check function, so I'll just return true. But if it is someone else, then okay, I will run the check. And since this just uses the default implicit objects in Scala, you can define as many values as you want for the scope object, as it's just algebraic data type. You can just extend that trait and define your own values. So I am going to talk about Vision, which is a company that I founded with these two gentlemen a while back. The customer pitch for this company is essentially, we say, it is the one place for musicians to do everything. It gives you a bunch of tools for writing to recording to touring, and we integrated this privacy approach to this code base because it was the largest code base that I have access to, where I don't have to go through a bunch of letters to get approval to try something out. But the advantage of having all of these in one place is that we have tremendous amount of data to help musicians optimize their project cycles. So if you're booking a tour, now your merchandising is on our platform, your ticket sales are on our platform, and your social media stats are on platform. So we can say something like, okay, people in Berlin, Germany, spend more money on your music, on your products, but people in Cologne spend less. So we can essentially optimize the best place for you to book your tour so that you will maximize attendance. And when we have this much data flowing to music labels, we have data flowing to managers, we have data flowing to PR agents, we need to be very careful about who sees what. And we integrated this privacy approach into Vision. So the compiler plugin has a total of 15 phases, and we saw a total of 12.4% compile time overhead over the raw application. What raw application means in this case is that you don't care about anything. There are no privacy checks, no brute force if statements. You'll just accept paying all the fines, so you don't do anything. And 7.8% compile time overhead over the brute force approach, where you have just a bunch of if statements distributed all over your application. And we saw 39% runtime overhead over the raw application, and just 11% runtime overhead over the brute force application, which is significantly lower than all the information flow control approaches. In terms of how much work the developer needs to do, this code base initially had almost 11,000 lines of code. In order to integrate this fully into this code base, we just had to add 180 lines of code and change 251 lines of code, and the total change is essentially around 4%, which is a very, very small amount. I'm going to quickly talk about the limitations. There are a few small limitations, like you cannot rename your imports. This is because of how the copying and the policy exploration works. This is technically possible. I just didn't have time to do it. I might eventually. We don't support private fields. When things get copied, they automatically get copied as public fields. Again, this is something that can be easily fixed. There is an interesting question of serializability of these containers. It would be amazing to be able to serialize these and then just send them over the wire, so whatever service is receiving this data receive them in essentially wrapped form. This gets into the open problem of functional serialization. How do we serialize services? How do we figure out the correct variables and things like that? If you were at the Unison talk, they have a great approach for doing this. It is not very easy to replicate this in Scala yet, but maybe one day when the language evolves a little bit more, I will give it a shot. And I'm going to leave you with an interesting question about async policies. So we said that our user data, user preferences live outside of our application. So we need to go and fetch it every single time. So technically, if we're being more correct, our check function doesn't return a Boolean. It returns some like IO of Boolean because it is concurrent. We don't know when that data will come back. Now, if I have a method that returns, for those familiar with the tagless final approach, returns f of a, and at some point, this method, the result of this method, will get policy protected. How do I know what f is? more precisely, how do I know what I should be protecting? Do I wrap the entire F in a policy, or do I wrap just the data that this computation will eventually return? Because F can be a list, and if it's a list, then I can just wrap the entire thing because I want to protect the entire data. But if it's an effect, like an I/O, then what does it even mean to protect the entire computation? This is an open question in both security and programming languages research. Racket people are looking into it, like what is a contract of a computation? What do we even want to restrict on a computation? This is something interesting to think about. In our compiler plugin, we use a sort of hacky method, like previously knowing what the values of that F can be. You know, it can be a Monix text, it can be a cat's IO, it can be a future. So we have some hard-coded logic to work around this, but in a generalized sense, this is actually very difficult to do. That is all I have. I think I have 2 or 3 minutes, so if there are any questions, I can take them here, or I will be upstairs for questions later.
Is it open source? Can we find it on GitHub?
I can make it, it's a private repo where I can make it public after I remove my delightful comments wrestling with the compiler. So just send me an email and I'll make it public. All right, thank you very much. And that's it.